We use it every day and we certainly rely on it. Although cryptography began thousands of years ago, mathematical analysis of encrypted communications has effectively altered the course of history.
The most important Japanese code in World War II was used by the Japanese Navy. And the breaking of that code turned out to be the most significant source of intelligence information available to the Allied forces. Japanese Navy made several fundamental blunders in the development of the code. Instead of having 100,000 possible code book entries, the maximum number you can have was 33,334, because that's the number of multiples of 3 with 5 digits. That turned out to be an absolutely critical blunder, because it enabled the codes to be broken steadily in time for the famous Battle of Midway in the middle of 1942, so the American Navy knew exactly what the Japanese battle plan would be.
The trap is sprung. The invasion forces were hit and hit and hit again.
In World War II, the Germans needed a mechanism to automate cryptography. The invention of the Enigma, an electromechanical rotor machine, made it easy for operators to just type in a daily key to encrypt their message, which the other end could then decrypt. The clever mathematicians at Bletchley Park in the UK, including Alan Turing, the father of computers, managed to break the Enigma.
I'm the head of the Crypto Mathematics Research Discipline in the Defence Science and Technology Organisation, DSTO. And our role is to support defence research into cryptography and cryptanalysis to support defence future security and Australian national security. Defence, to do its role, needs to ensure that they can communicate effectively.
Yeah, cheers, thanks.
And securely.
Of course, on is maintaining orbs on the vicinity of
Troops overseas on dangerous operations need to be able to communicate to their base. And so all of those links need to be real-time and secure, otherwise people's lives are jeopardised.
Tango 4252.
What came out after World War II, which revolutionised cryptography, was a system called RSA, the initials of the 3 people who developed it.
So traditionally you had symmetrical encryption, you had to have the same key. The breakthrough really was in coming up with this idea of an asymmetric algorithm where you needed 2 different keys, one of which you could make public, the other one, as long as you kept it secret, you could be sure that the communications people were sending you were secure. It's quite easy to multiply 2 numbers together. It is a much harder problem to look at a huge number and ask what 2 numbers were multiplied together to form that number. So to make the RSA problem as hard as possible, you create these 2 secret prime numbers, you multiply them together, you get a very big composite number, which means it can be broken up as a product, and you're the only one who knows how to do that.
Pierre de Fermat proved his little theorem in 1640. It's an important component in proving that the RSA cryptography works.
I'm a principal security consultant in the information security group at Westpac. Cryptography in banking is very important in today's society. It gives us the ability for us to trust the customer, to manage risk, to reduce fraud. If you look at a modern credit card, you'll see a little gold chip on the card, and on that chip is special circuitry that enables information to be encrypted and decrypted in a very safe way. The beauty of modern cryptography is that it's invisible. An example of that would be using internet banking. The customer's browser and our internet banking server talk to one another. All communications between the browser and the server are encrypted. For certain customers of Westpac that transact in very large amounts of money, we augment the internet password with an additional layer of security. we use an RSA token device that we give to the customer. You'll see 6 numbers displayed on the front of that token. The number is derived from the time of day and also a secret encryption key that is unique to every token. Those 6 numbers change every 60 seconds, and that number can only be used once by the customer to log on or authenticate with our server. Without that mathematics, the cryptography would not be possible. And without that cryptography, modern banking would not be possible.
Our business is the application of cryptography to solve real-world problems on high-speed optical communication systems. So our customers tend to be people who care deeply about the security of their information. That includes military and defence type organisations, all branches of government, in the financial sector, in the industrial sector, in the mining and infrastructure. And we have to use symmetric rather than asymmetric encryption algorithms because they're much faster. We have to transfer securely the encryption key from the sender to the receiver across the network. And to do that, we do use asymmetric RSA encryption in our products. We use AES 256-bit symmetric encryption to encrypt the data keys, and we use RSA encryption with a key size of 2048-bit to securely exchange those data encrypting keys across the network. Challenges aren't going away. Networks are getting faster, the bad guys are getting cleverer. It's really a constant war between the code makers and the code breakers, so we need the best and brightest minds to help us with that problem in the future.